Hey everyone, how are you today? I'm having lots of fun playing with shapes again. I've just drawn this circle over here, which I shall call Bennett. I can describe Bennett mathematically pretty easily. I can say that the center of Bennett is the point 0, 0, which is technically also named Bennett since circles are usually named by their center. Then, for all the points on the circumference of the circle, I can draw a right triangle like this, where the hypotenuse goes from this point to the center, and this line here is on the x-axis, and this line here is parallel to the y-axis. Then, if the coordinates of this point are x, y, the length of this side is x, and the length of that side is y. Can you see why? We also know that since this is a circle, this side has to be the radius. If we use the Pythagorean theorem here, it tells us that x squared plus y squared equals the radius squared. This is true for all the points on the circle, so we can describe Bennett by saying that it's the circle represented by the equation x squared plus y squared equals the radius squared. But this description makes Bennett sad. He thinks that the equation isn't a complete description of his personality, because he has inner depths that x squared plus y squared equals the radius squared just doesn't describe. And the circle is right. For example, this equation doesn't say anything about how I drew the circle. Did I start here, or did I start here? Did I draw the circle slowly, or did I draw it quickly? In order to answer these questions, I need to introduce some wibbly-wobbly, timey-wimey stuff. Instead of just saying which x-coordinate matches with which y-coordinate, I'm also going to say what time I drew that exact point, which I'll represent with a clock. But it's kind of hard to have a good equation that relates three whole things, so I'm going to keep it simple and just compare two things at a time. I'll start by comparing the time and just the x-coordinate. So I start here, and when I first start, I'm putting more effort into going up than going sideways, so I'm going sideways slower. But I start speeding up as I get more sideways, and then here I'm slowing down again, and now I'm going backwards. How am I ever going to describe this? Well,
Mama said, don't give up, it's a little complicated.
Remember back when we were drawing a circle of trig functions, and we figured out that the x-coordinate was the cosine of the angle, and the y-coordinate was the sine of the angle? If we say that we're moving at 1 radian per second, we can use this function directly. The x-coordinate can be the cosine of the amount of time that has passed, which is the same thing as the angle in radians that we have reached. And the y-coordinate can be the sine of the amount of time that's passed, which is again the sine of the angle that we have reached. With these two equations, we have a much better description of who Bennett is as a circle. We know that I had to start drawing it at this point here, and we know the exact point I was at 3 seconds after I started, or 2 seconds after I started, or 5,000.5 seconds after I started. Can we also describe a circle that starts on this side? Or a circle I'm drawing twice as fast? Or a square? I'll let you try to do those, but I'm going to look at something I find more interesting in parametric equations. The fact that you can combine the x-coordinates and the y-coordinates of two different sorts of equations to form a new and weird-looking graph. What if I want the x-coordinates from a y equals x cubed graph? Well, if I use the parametric equations x equals the time and y equals the time cubed, that forms the graph I want, but not at a useful speed. Because it's moving across horizontally at a constant speed, it's moving along the line faster and faster as the line becomes more vertical, since the time it must take to get from 3 to 4 has to be the same as the time it must take to get from 1 to 2. But you can see here that the line is much longer from 3 to 4 as it is from 1 to 2. We want to find some equations that make me draw a line in the way that I'm not moving any faster here than I'm moving here. And after some brief Googling, I couldn't find a simple way to do this, so that might be something interesting to look into later. For now, though, I'm going to change this to y equals the time and x equals the time to the 1/3 power to keep the timing more interesting on the x side so that I can use it with some other equations. Can you see why these parametric equations create the same graph as the parametric equations I had before? So I'll take the x-coordinates from this equation and I'll combine them with a cosine graph, where the y-coordinate is the cosine of the time. I graphed this on Desmos, and that looks pretty cool. If I let the time get to an even larger number, like 9,000, I got an even weirder result. I'm not sure if this is due to the calculator approximating this weirdly, or if it's an actual property of the graph that it looks like this when t gets to such a big number. But if you try to figure this out, please let me know what you find. Parametric graphs are another thing that's just really fun to play around with, and again, playing around with it is the best way to get a good understanding of what's going on. I'll put a link to something I found on graphing parametric equations on Desmos, so you can just mess around with that and see like what cool things you can create. Let me know what cool designs you make, by the way. But for now, that's all. See you next time!